In this next video, we're going to talk about transformations on the response variable. So in the previous video, we talked about this option of transforming the predictor or a predictor variable in our model in order to better fit the relationship that we see between that individual predictor and the response variable. However, there's going to be some situations where it might be more appropriate to transform the response variable because maybe we have just one predictor, maybe we have a lot of predictors, but we might have this problem that the residuals of our fitted model are non-normally distributed or at least don't have some kind of constant variance when we look at kind of the fitted value. So here's an example of a residual plot where we clearly see non-constant variance in the residuals as our fitted values kind of increases here. Now we could actually have the relationship the opposite direction as well, right? We could have kind of a closing in cone. In other words, as the fitted values increase, the variance is getting smaller and smaller, that the variance is a lot higher when our fitted values are lower. That's also an issue that could happen. Though I feel like this is more, this particular direction is commonly seen, even though both of them would be problems that we'd fix with similar solutions here. So yeah, because we might have multiple predictors, maybe we don't, but often we do, we're going to have to kind of go to the residual plot to see if we might have a residual issue that we would need to address. And so if the problem that we have is isolated to one particular predictor, not having a clearly linear relationship, a predictor transformation makes a lot of sense. Whenever it's one of these issues, we probably need to transform the response. And I have one extra screenshot here. Sorry about that. I think this is supposed to go onto the next page, which it is, but I think I left it here by accident too. So pretend that's not there. So here's an example of just a simple model. So again, we might have more than one predictor, but here's an example where we just have one. And we can see that the variance is not quite constant. The variance might be increasing here as our predictor increases, as our fitted values are clearly increasing. So that might be a problem here for our simple linear model assumptions. That's assuming the variance is constant at all conditional distributions of y given x. So one option we have is to transform the response variable and a log transformation, so a natural log. So if I say log in this class, I mean natural log all the time. A natural log transformation on the response will actually stabilize the variance in our residuals. That's just a transformation that usually makes that happen for us. We're not going to mathematically unpack logarithms in this class, so maybe you understand this, maybe you're a little bit rusty on what a log is and how this works, but just kind of trust that transforming the response by taking the log will often kind of equalize the variance for us in a model. So what we have over here is the same relationship, except that now it's the log of salary instead of just salary. And we can see now that we have constant variance, and we also have a linear relationship here as well. So that's also something that can happen with the log transformation, is that slightly nonlinear relationships can become linear as well. So expressed in another form, so right here we have the expression as the log of y as fitted by x. But what if we wanted to rewrite this equation such that we're left with just y on this side of the equation, and that we want to rewrite this side of the equation so that we can do that? Well, we can do that. We just have to take the inverse of the log, which is going to be e, the exponential of each side. So if I take e to the log of y, I'm just going to get y. And then if I take e to the beta naught plus beta 1 xi plus epsilon sub I, I'm going to get some term that looks like this. And there's actually kind of a step that's skipped here. This would be beta naught plus beta 1 x sub I plus epsilon sub I, right? That would all be kind of in the same term. But if you remember kind of rules with exponentials, I can actually break off these different additive exponents into different e terms. So I could also rewrite this as e to the beta naught times e to the beta 1 x sub I times e to the epsilon I, and that is an equivalent expression. So that's kind of what's going on here with this particular expression, is just the epsilon got broken off, but this is still the same thing. It's just represented a little bit differently. Right, and this is fine. This is just an expression of y with our model. And so if we wanted to represent this equation, we certainly could do that. Now, one thing that I will kind of mention, we talked about in this previous video what makes something a linear model. And we said that a linear model is anything that can be written as a linear combination of predictors. So you might be kind of looking at this wondering, well, you know, is this a linear combination of predictors? The answer is no. However, this expression over here is a linear combination of predictors. So if we have the expression, or I guess I should say this is an equation now with both sides, if our equation is such that we have to transform the response, then we can still, in this case, write this as a linear combination of predictors, and we can call this a linear model, even though if we transform y back into its original units, the equation is no longer linear in terms of the predictors anymore. But that's okay. We still call this a linear model because we can write an expression where that's true, and we can use that for purposes of inference. We will talk about, I should mention though, that there is this term called a generalized linear model, which kind of links this together a little bit better under what is a linear model and this idea of what's called a link function between the response variable and this linear expression. So we will kind of return to this again later and hopefully make a little bit more sense of it when we get to chapter 17 and talk about generalized linear models. But for now, just kind of know that even though we are having to change the expression of the response variable, as long as we can write the predictor side of the equation as a linear model, we can still call this whole process a linear model, and that's okay. So coding response transformations is really the same as coding predictor transformations. I'm just going to write my LM function and write the log of the response here, or whatever transformation I'm doing, as predicted by, and then list my predictors out as normal. So again, I can just kind of code that into the LM function that I'm running. And then we just have to keep in mind that the fitted values that I'm getting, so my beta hat coefficients, are fitting this model right here, where I have the log of y equals this intercept plus this slope value times x. Now mathematically, if I wanted to return back to the original units of y and make that transformation now on the predictor side, then I just have to take the e, the exponential of these terms. And so then I would just have my y hat would be the exponential of the intercept times the exponential of the slope times x. So something I'll kind of mention, it's not super important because we're mostly going to be doing these with R anyway. But what does the slope value represent in terms of a change in y? So for each 1 unit increase in x, what does this tell us about our expected change in y? Because since this is no longer an additive term, I can't just say that we're expecting y to increase by 0.079 for every 1 unit increase in x, because now this is all wrapped up in this multiplicative expression. So I kind of want to mention how we'd interpret the slope here. For every 1 unit increase in x, there we go. We expect y to be multiplied by e to the 0.079. So in other words, if we have some value for y at a particular x value, maybe it's a y hat value, right? Kind of our fitted value for y. So maybe we could even put that in there and that would still be fine. For every 1 unit increase in x, we expect y hat, or actually, well, if I say expect, then I don't really need to put the y hat. We expect y to be multiplied by e to the 0.079 in reference to the previous fitted value for the previous x value. In reference, so I'm just going to add that part. Which is a really kind of a mouthful, right? Like you read this sentence and it's kind of hard to like make sense of what's going on. But what we're really trying to just say here is that this slope value represents kind of this multiplicative change, this expected change in y for a 1 unit increase in x. So if we have a particular y value at a particular x value, and we want to know what happens to y if we add 1 unit to x, we expect y to change by being multiplied by e to the 0.079 as a result of a change in 1 unit increase in x. So it's a lot harder already to make sense of this, and that's why linear models are a lot easier to work with. And so obviously if we kind of transform this back into y equals some nonlinear expression, interpreting the coefficients is a lot trickier. But that would be the literal meaning of these values, of this slope value in predicting y. All right. So that was what's called a log transformation on the response variable, which is fine for a lot of situations. But a log transformation isn't going to fix everything. It's not always the solution when we have a residual issue in our model. And so that's why we have kind of a family of transformations that we can use to determine the most appropriate response transformation for a given situation. So BoxCox transformations use kind of a mathematically complicated system, but basically we're taking what's called the log likelihood representation or log likelihood function, and then we're finding a value called lambda that maximizes that log likelihood function to find a response variable transformation that makes the residuals most close to these particular assumptions. So we're not going to mathematically unpack how that works and why this is the expression that we use. We're just going to trust in this class that this is something that we can commonly use to find an appropriate transformation for the response variable. And I will kind of mention two special cases here. If we do what's called a BoxCox transformation and find that lambda equals 1 is a very kind of highly valued transformation option for lambda, that means that we really don't need a transformation. So a lambda of 1 corresponds to no real transformation in y, because if you think about it, y to the 1 is just y. So y minus 1 divided by 1 would just leave us with y minus 1. So I'll kind of mention if lambda equals 1, then we're going to have y minus 1 is our representation for the response variables. In other words, we're just taking 1 unit away from all of our y values, which just corresponds to really not transforming y at all. We're just taking the scatter plot and just going, doop, we're just taking it down 1 unit, which is not actually doing anything. It's not actually making the fit any better than what it was. I'm way over here. I'm going to put myself over here in this corner for a second. So that option really is no transformation. So if lambda equals 1, we really don't need a transformation at all. We can just leave y in its original units. The other special case here is when lambda equals 0 is our best fit for this log likelihood function that's being fit. And that means that we should actually do a log transformation. So I'm slightly in the way here, so maybe I'll go over here for a second. So if lambda equals 0 is our result from doing a BoxCox transformation, then we should do a log transformation on the response variable as being the most appropriate here. In all other cases, we would just plug the given value for lambda into this expression. So we would take y to this value of lambda minus 1 divided by lambda. So here's an example of what we're talking about. So let's say that I have a residual plot. So here it looks like I have a residual plot where my variance isn't quite constant. but it's really not that bad. The residuals look pretty normally distributed, so there's not really a whole lot wrong here. And sure enough, if we do a BoxCox transformation, it actually looks like lambda being about 1 looks fine, meaning that I really don't need much of a transformation here, and that maybe no transformation is fitting the residuals about as best as I can in this situation. So there is this function called BoxCox, which makes this really easy for us. It's contained in the mass package, so if you just kind of library the mass package and then run BoxCox on whatever model that you've created, you can also add this plotted equals true argument as well if you want to see the plot, so not just try to output a value, but actually kind of see the range of values that are appropriate. That's usually the best way to do this. And so we can kind of see that 1 is around the center of our estimate. There is kind of a confidence interval for what lambda could potentially be best as, a little bit below that and a little bit above that, but certainly 1 is very much in this sensible range here. We can also zoom in on a particular region as well to see better. So if I kind of add this lambda equals argument and then choose a sequence within a range that I'm interested in, then I can just kind of see better that yeah, 1 looked pretty good. I mean, I guess we could also pick about 0.9293, but usually at that point, we'd round to kind of a nice number. So we don't usually try to find to the decimal, like especially to like multiple places here, the lambda value that makes most sense. We're usually going to round to either a whole number or the nearest 10th of a decimal place in most situations. Now here's a different situation where a transformation is probably needed. So here we see that the residuals are super non-constant and definitely don't seem to be normally distributed around the best fit line. So here's a case where we run BoxCox, and we see that the ideal lambda value is somewhere around 0.3. Again, it's we could try different lambda values. It's kind of hard to know with a small sample of data. We're going to get a pretty large confidence interval in those cases. The more data we have, the more we should see that confidence interval converge pretty close to a highly valued lambda. But here we definitely see a lambda value somewhere around 0.3 should help fix this residual issue about as best as we can. And so sure enough, we transform y into being y to the 0.3 power minus 1 over 0.3. And we're going to plug that into our LM function. So notice it's a little bit tricky with the parentheses because there's a lot of parentheses. But if we take our response variable to the 0.3 power minus 1 divided by 0.3, as predicted by these other predictors that I'm using, I now actually have a pretty good looking model when I make that residual plot. I have pretty constant variance across this range. The data looks pretty normally distributed. I don't have a lot of data in this range right here. I definitely have a lot more data over here, a little bit of data over here, but the residuals are pretty good, which means that I probably have an appropriate linear model meeting the assumptions that I need here. Now, it is certainly possible that you might choose to transform both a predictor and the response variable for a particular model. And it's kind of hard to know when that's necessary, other than just knowing that you could try just by trial and error and notice that you're still not making a lot of progress. So here's an example where if I take the log of this predictor and this response, that's when I get a pretty good linear fit with constant variance, normally distributed residuals. Whereas if I just take the log of, say, the response variable, it's not quite there. I still have a little bit of kind of bad fit going on here as well. So just kind of something I'll mention is that you might choose a transformation on both, and that's just kind of a trial and error thing that you'd have to try one and try the other and see that maybe it's still not enough, and trying both might fix that issue. Which really leads to this larger conversation that I can't necessarily tell you what you should always do, and that is when to use which transformation. How would you know when one is appropriate and as opposed to just trying everything? And so there are some guidelines here that we've mentioned already, that if the issue is largely just a nonlinear fit between a particular predictor and the response, then a predictor transformation is probably most sensible. If the residuals are not normally distributed or non-constant variance, that's a situation where response transformation is probably needed, that a predictor transformation is probably not going to fix that by itself. In general, though, you just have to try different options. That whenever you have assumption violations like that, usually doing a BoxCox transformation on the response can find a lambda value that makes this work. Maybe that's enough. Maybe a predictor transformation in addition to a response transformation fixes that issue, but you just kind of have to try things. And then a last point here that I'll mention is that when modeling for explanation, so if your goal is to try to understand a relationship between a set of variables, you want to keep things interpretable. You don't want to add more complexity than you have to. So a BoxCox transformation, as an example, is going to be kind of a convoluted transformation of your response. A log transformation is a little bit simpler to understand and go between res. This weird power change divided by some number is not quite as sensible to work with. Same again with predictor transformations, where I can keep adding more polynomial terms or more complex transformations of the predictor, but at some point the model just doesn't make a lot of sense for me anymore, and it's kind of hard to interpret. So if your goal is explanation, then it is kind of a balance between having appropriate assumptions for your residuals and trying to have relatively normal constant variance residuals, while also trying to keep the model sensible. And you may not get everything that you want in that case. You may not get, like, you might still have a little bit of an assumption issue, and that's okay if you're doing it for the purpose of interpretability and keeping the relationship sensible. So I'll just kind of leave that as a last point. Use trial and error, and think about your goals, and how complex you're okay letting your model be.